Hopefully everyone can see and hear me. Yes. Okay, good. Let's go back. Hello, hello, welcome. Hopefully everyone can see and hear me. I can't see my own video for some reason. So I hope that you guys can see it, but it's for whatever reason not appearing on my screen. So hopefully everyone can see me. Please feel free to say hi in the chat. This is our Sunday session, A-level chemistry, Sunday session, revision session on dynamic equilibrium. So yes, please feel free to say hi in the chat. Oh, I'm going to fold my screen over, which sometimes makes my camera turn itself off, which I think it just has done. I'll try that again. Yeah, okay, I'm going to turn my screen over so I can write on it, but yeah, it does sometimes. I like to turn my screen off, the camera off. Oh, now it doesn't want to turn on. Sorry. Oh no, there we go. I think I'm back. Sorry, it didn't want to turn itself on then. Hello, welcome. Please feel free to say hi in the chat. Welcome to what's going to be my final YouTube class for Snap Revise. This is an A-level chemistry revision class on dynamic equilibrium. Hello, Kama, hello. Nice to have you here. I'm going to give it a couple of minutes in case anybody is running late and wants to appear in a minute, but then we will get started. I've just realised that my screen is being slightly snuck in on. That's a bit irritating. Let me move that over there. Okay, that's a bit better. Yeah, there we go. Okay, lovely. But welcome. So this is an A-level chemistry web class on dynamic equilibrium. There are loads of others in the Snap Revise YouTube class. If YouTube, what's it called? This section of YouTube. What is that? Why is my brain gone blank? If you have a look through the rest of Snap Revise, there are lots of YouTube videos that you can watch from previous sessions that we've done in chemistry, physics, and maths. Hi, Isaac. Lovely to have you here. This will be my last one with Snap Revise, so I've got not sure what's happening next month. Usually they do one maths, one physics, one chemistry, one biology a month with different tutors. So I don't know what's happening next month to the chemistry ones. I haven't been informed, but keep an eye out for the schedule. I'm sure it'll appear somewhere if and when there is another teacher. But so this is my final one for Snap Revise. So we'll get started in a second. We're going to need, or you may choose, actually don't need, you may choose to download the slides. They should be in the description, so you can follow along if you would like, or you can save it for later. You can just listen, but the more you engage, the more you're going to get out of it, because that's just what happens. That's what usually happens when you're learning. The more you engage, the more you get out of it. Right, let's get started. So this is a little bit about me. I am / was the chemistry teacher for Snap Revise, but this will be my last YouTube class for Snap Revise. I'm going on to do other things. I have a PGC in science, but specialising in chemistry from Oxford. I've been teaching for blipping ages now, over 9 years. I can teach all 3 sciences. And a bit of maths as well, but chemistry is my favourite. Chemistry is the one I've got a master's degree in, so it is my fave. Okay, so for this session, our plan is to understand the concept of reversible reactions and equilibrium. We're going to look at Le Chatelier's principle and then we're going to look at applying Le Chatelier's principle to different changes. A lot of this is actually GCSE. So although, or let me rephrase that. A lot of this is building on what you do at GCSE. So hopefully a lot of it is you recognise and is kind of revision, because you already know what's going on. The only difference at A level is that they like you to be able to explain it, and you need to be able to show kind of the connections between the different explanations. So you need to be able to explain every level, as it were. So we're going to look at that, and we'll look at the phrases that it's good to use, and hopefully get on to doing some exam questions as well. So what we're not going to look at, though, is equilibrium constant. That links very closely to this topic, but we won't have time to cover that as well, so we're not going to look at that. Now, if you're an AQA student, it's these sort of spec points that we're going to be looking at today. If you're OCR, it's these, and if you're EdXL, it's these. So feel free, if you've got a copy of the slides in front of you, feel free to flick back to those if you are unsure about how this applies to you, or whether or not you want to see if there are any specific keywords you might want to be aware of. Your specification is your best friend when it comes to revision. Okay, so let's have a think about what we already know about this topic. So what in chemistry, what do we count as a closed system? In order for dynamic equilibrium to occur, we need a closed system. So what is that? Feel free to pop something in the chat. I'll give you a minute or so to have a think, and then pop something in the chat if you want. And then I'm going to give you an answer. So what is a closed system? What counts as a closed system? So you might find sometimes that you find that physics has a slightly different definition, or actually in some places in applied chemistry, they have a slightly different definition. So you just got to be slightly careful, but a closed system, in order for dynamic equilibrium to occur, means that no energy or matter is transferred from the system to the surroundings. So no, energy or matter is transferred from the system to the surroundings. Now, the issue is that sometimes we do like to talk about, we like to ignore the energy part of it, because you can create a closed system when there can be energy transfer. However, within chemistry, if you try and think about closed systems being there's no transfer between the system and the surroundings, then you've created a closed loop, you've created a closed system. That's usually what we're referring to in chemistry when we talk about a closed system. Hi, Tafara. Yeah, lovely. Fabulous. Okay, we'll come to the last two in a second, but what about the system and the surroundings? If I'm talking about the system, what am I talking about? And if I'm talking about the surroundings, what am I talking about? So it's good to have this differentiation in your head, because the system, when we're talking about the system, I'm talking about the matter I'm studying. That's usually the reactants and the products of a system. So the system is the matter that we are studying. And then the surroundings is everything else, any other matter. And the surroundings can also be the solvent that the reaction is sitting in. Yes, exactly. The environment is the surroundings. So any other matter are your surroundings. So again, that could be the beaker that the reaction is happening in. It could be the solvent that the reaction is happening in. It could be the atmosphere, it could be the lab that you're sitting in, whatever, that is your surroundings. So the only thing that we count as being the system is the actual matter that we're studying, the actual thing we're interested in, the actual stuff that's involved in the reaction that we're looking at. Okay, go on then. Endothermic and exothermic. What are they and how do we tell them apart? What is endothermic? What is exothermic? And we're usually talking about processes or reactions, but what does it mean if something is endothermic? What does it mean if something is exothermic? If you can, pop your answers in the chat. If you're not sure, we'll go through it in a second. Nice, that's a good way, Isaac, of thinking about it. So exothermic needs heat. Sorry, endothermic needs heat. And if you want to think about it like that, you could link the N in endothermic to needs heat, if you need some way of remembering which one's which. And then exothermic gives off heat. Now, the way that I've always remembered it is endothermic, energy enters, and exothermic, energy exits. Yeah, lovely. Endothermic means heat is taken in. Very good. So if we're going to use scientific speak, which we probably should when we're talking about these different keywords, we're going to say there is a net heat transfer from, if it's endothermic, energy going in from the surroundings into the system. So from the surroundings into the system. That is endothermic. And then exothermic, heat is taken out. Good. Heat is released to the surroundings. Very good. Energy is lost. Very nice. Well done. Yeah, good. Well done, guys. So exothermic, again, energy is exiting. So that means there is a heat transfer. Oops, I can't spell transfer. So if energy is exiting the system, it's got to be transferred from the system to the surroundings. To the surroundings. This is why it's important to get an idea of what we mean when we say the system, and what we mean when we say the surroundings. Endo means in and thermic means heat. Yep, good. So heat is absorbed into the system, while exo means out and thermic means heat, so heat is absorbed. Exo, heat is released. Yes, well done. Good catch. Yeah, good. Correct. So exo exits or outside of, so energy is leaving the system. Lovely. Right, let's think about dynamic equilibrium then. So in order for there to be a dynamic equilibrium, we need a type of reaction to occur. Now, irreversible reactions is what we used to think of at Key Stage 3, usually when we were thinking about reactions. Actually, we do talk about some reactions as being irreversible, as being one way, but that's just because the reverse reaction has such a high activation energy or is so unlikely to happen. If you are a year 13, if you're going into year 13, you may have looked at Gibbs free energy, which talks about whether or not a reaction is likely to happen. And it discusses entropy as well as enthalpy, etc. And it might be that actually it's very, 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 very unlikely that the reaction is going to go in the backwards direction, in which case we say it is an irreversible reaction. It's a one-way reaction. The reaction goes forwards only. Reaction goes forwards only. But like I say, that's actually very unlikely that you will find there are some reactions that we say are irreversible, but there's just a lot less likely that they are actually irreversible. It's probably just that the reverse reaction is just very unlikely to happen. Good. Reversible reaction is a two-way reaction. Lovely. So that's the reaction can go both ways. Goes both forwards and backwards. And again, just to reiterate what that means, as in A and B can go to make C and D, but also C and D can react to make A and B. So we can have a forwards reaction and we can have a backwards reaction. Hopefully this isn't new. And an example that you may or may not have met yet, but you definitely need to know for your A-levels is the reaction of, let's do R, no, let's do it facing the other way. Sorry, I'm just changing my mind. Let's make that R1 and R2. This reaction, the reaction of a carboxylic acid and an alcohol. R just means an alkyl group, just means a substituent group. And I've put R1 and R2 to suggest that they could be different to one another. They don't have to be, but they could be different. R1 could represent one thing, R2 could represent something else. So maybe methyl and ethyl, or propyl and butyl, or whatever. And they're going to react together to make sure I get it right around. That's R1 there, R2 there, and ester releasing water. So this is a reversible reaction. In the forwards direction is a condensation reaction. And in the reverse it is hydrolysis. Oh gosh, I can't spell. Hydrolysis. There we go. Is hydrolysis. So that's a reversible reaction. One that is very reversible because we can encourage it to do both directions. Oh, sorry, I just moved my mic. Let's put that back. Okay. Yes, the Haber process, nice. That's also a very good reversible reaction that we come across quite often, actually. So yeah, another nice one. Well done. Okay, so let's have a look at representing dynamic equilibrium. So there are two things that are key for recognizing when dynamic equilibrium is occurring, or two things that prove a system is at dynamic equilibrium. What are those things? What are the two things that mean our system is at dynamic equilibrium? Do we know? No net change. What do you mean by that? Can you be a bit more specific? You're absolutely right. Can we be a bit more specific? No net change of what? Lovely. Good. That's another one as well. So you've said two. We just need to be a bit more specific on the first one, but I'm going to go with your what you said second. I'm going to write down first. So the rate of the forwards and backwards reactions are equal. Or you can say the rate of the forwards reaction is equal to the rate of the backwards reaction, or the rate of the forwards reaction is the same as the rate of the backwards reaction. I prefer to use the word equal because the word the same can be a little bit confusing, and it also isn't specific enough for me. I feel like we need to be very specific. We are saying that they are equal. The rate of the forwards reaction is equal to the rate of the backwards reaction. They must be equal in order for our system to be in dynamic equilibrium. And the second one, lovely, is that the concentration of the reactants and products does not change. That's really good. So there's no net change of the concentration of reactants and products. So the concentration of reactants and products stays constant. Again, I'm using that word very specifically. I'm saying it stays constant, as in they don't change. I'm not, and I definitely do not recommend using the word the same, stays the same here, because you could be suggesting that the concentrations of the reactants and products are equal, and they could be equal, but it's very unlikely. It's more likely that they are different, but they are staying constant. So they're different to one another, but they're staying constant. So the key is that they're staying constant. So that's why I have particularly used those words there. So the fact that they're equal and constant, and I don't, oops, then I don't have to think about, oh no, that's not supposed to happen, sorry. Stays constant, sorry, I didn't mean to delete that. So I've meant to use those words very specifically. Yes, I know. Results day is coming up soon, isn't it? Scary. It'll be fine. It will be fine. Right. What is it, or what aspect, where on this graph has my reaction between NO2 and N2O4? When has it reached dynamic equilibrium? At what point, what aspect of the graph could you tell me, or where can you describe where on the graph it is in dynamic equilibrium, or dynamic equilibrium has been reached? How exciting. Very, very exciting. So what aspect of the graph, do we know what aspect of the graph shows us that dynamic equilibrium has been reached? Is it where they cross over? Or is it, well done, Mike, the dotted green line? It is that dotted green line. Why? It is. This is where equilibrium has been reached. How do we know? We were talking about point 2 there is the concentration of the reactants and products stays constant. And it is at that point that my concentrations have started to stay, yeah, lovely, well done, Mike, that they have started to stay constant. Which one's which? So red, this is the one that comes up from the bottom. Blue, that's the one that comes down from the top. Which is reactants, which is products, and how do we know? So the one that comes up from the bottom, that's our red line. Which is reactants, which are products. We've got NO2 and N2O4. How do we know which one's which? Red is reactants, we reckon. The green line is absolutely correct, Tafara. But can you tell me which lines representing the reactants and which is the products? Yes, well done, Isaac. The red needs to be our product because because it starts from the bottom and it's being produced. Oh no, it's done it again. It's being produced. So we have to have started with none of it to begin with because that is our product. So that's our N2O4. And then the thing we've started with some of and is being used up until it reaches equilibrium must be our reactant. So that's the NO2. So it's a good thing just to double check. And the concentration doesn't change after the green line. So that is where equilibrium has been reached. And then if we wanted to, we could read off, that's a lovely straight line there. We could read off our graph and find out what our starting concentration, find out what our equilibrium concentration of product was and do the same for our reactants. Find out what their equilibrium concentration is. So blue is our reactant concentration because we've started with an amount and then it's decreased as it's been used up. And red is our product because we've started with none of it and then we have gained product. Okay, let's keep going. So let's think about Le Chatelier's principle. It's not an easy thing to do, but can you give me a brief description of Le Chatelier's principle? What is Le Chatelier's principle? How do we describe Le Chatelier's principle? What words do we use to describe Le Chatelier's principle? Anybody know? That's a nice, very succinct way of putting it, actually, Mike. Obviously, in an exam, we'd need to put more detail, but at least I get an idea, you know what's going on there. So, Le Chatelier's principle tells us how the equilibrium concentrations will react to changes in an environment. It will oppose the change. So when a system at dynamic equilibrium is, you can say subjected, you can say stressed, you can say put under stressed, you can say when a change is made, etc. So subjected to external change, the system will react to oppose the change. The system will react to oppose the change. Or you can say to minimize the effects of the change. Minimize the effect of the change. Or the stress, or whatever it is that you have, whatever phrase you've used. Reaction does the opposite to a change of a system in an equilibrium. Yes. Yeah, lovely. Well done. Okay. So I'm not talking about Le Chatelier's principle at the moment, although we will go on to look at Le Chatelier's principle in a second. But just thinking about positions of equilibrium, if we have got more reactants than products, we say the equilibrium equilibrium is the left. If we products, then we say the equilibrium is shifted to the right. Equilibrium is shifted the now about I should list an exam question first. So one of the things that I would highly encourage you to do, and your teachers probably do this as well, is to, as you're going through your revision and even as you're learning, you should take the opportunity to have a think about how you feel about the stuff you're learning. How confident do you feel? So feel free to share it with me. You can share it with an emoji if you want to, or is with a 1, 2, or 3. But just let me, if you want to, you don't have to, share it with me and let me know how you're feeling. But if you don't want to share, just have a think to yourself, how did you find all of that stuff? Is that stuff, yeah, you already knew that, that's all good. Was it okay? You probably could do a couple of exam questions on it, but maybe you would need a bit of support with it. Or was it all awful? And if it was all awful, fair. That probably means you need to go back to your basics a bit and make sure that you're confident with your basic core chemistry, and then you can build on it from there. Okay, lovely. Let's keep going then. Let's have a go at this exam question. So, speaking of the Haber process, ammonia is manufactured by the Haber process in which the following equilibrium is established. N2 plus 3H2 goes to make 2NH3. Give 2 features of a reaction at equilibrium. Now, you don't need to write it all out, but can you just give me the suggestions? How do we recognize a reaction at equilibrium? What are the 2 features? It's 2 features. How do we recognize that a reaction is at equilibrium? One is that the concentrations of reactants, lovely, well done, reactants and products remain constant. That's why we call it a dynamic equilibrium, because the reactions are constantly happening, but they're happening at the same rate, which is going to be feature 2, because they're happening at the same rate, the concentrations stay constant. You've got the same amount of your reactants being used up to make products as you do your products being used up to make reactants, and therefore it looks like there's no change happening, even though there is. Lovely, good. Fantastic. So also the forwards and backwards reactions. Oh, my pen's being a bit weird. Let's try that one. Right then. It's better. Forward and backwards reactions occur at I'm being lazy now. At the same rate. Fantastic. Really good. Yeah, well done, everybody. Fabulous. Okay, so let's think about Le Chatelier then, and how we can affect the position of equilibrium using Le Chatelier, or what happens with Le Chatelier. So, the effect of concentration. Again, this is something that technically we do at GCSE. You're just expected to know what happens. You're not expected, so you're just expected to be able to describe what happens. You're not actually expected to be able to explain it in a huge amount of detail. At A level, we do need to be able to explain what is going on. So you're going to need a little bit more detail, and there's going to need to be an explanation in there, not just a description. We have to be able to say why. So for any reactants or products in solution, the position of equilibrium will be affected by changes in concentration. So for example, here we can ignore B and D because they're not in solution. They are solid. But if we were to increase the concentration of A, so hopefully everybody knows, but those square brackets means concentration of. So an increase in the concentration of A, what will happen to our system in equilibrium? What is going to happen to the position of equilibrium? We don't know where it is to begin with, but we can talk about what happens to it. So what do we think? Anyone know? If we increase A, what's going to happen to the position of A? More products for, yes, fantastic. More products are formed as. So there's lots of different ways you can talk about it. You can say the position of equilibrium shifts to the right, to the products in the forwards direction. Any of those three would work. That's absolutely fine. So use whichever phrase you would prefer. They all mean the same thing. So more products are formed as the equilibrium shifts to, I'm going to say to the right rather than towards the products, because we've already used the word product. So I'm just, oh, no, sorry, moved it. Try again. Shifts to the right to, and we can talk about using up the excess of A, or we can talk about redressing the balance, however we want to phrase it. So more products are formed as the equilibrium shifts to the right to use up the extra A, something like that would work. So it's going to shift to the right. It's going to, we've added in A, and so the system is going to use it up. I kind of like to think about it, or I don't know if this will be helpful or not, but one of the ways I think about it is if your parents are making some dinner and they realize you've got lots of eggs, then you're probably likely to have eggs tonight because you're going to want to use up that extra egg that you've got at home. Or, you know, similarly, if you have you've got a really productive garden and you've suddenly produced a load of courgettes in the garden, or carrots, whatever it is. Say someone's gone out and picked a load of carrots and you've brought them in, suddenly you've got a lot more carrots than you usually have. So you're going to be eating carrots tonight. So you're going to be trying to use up those extra carrots. So in order to use them up, you need to do the reaction that's going to use them up. So in this case, we've got extra A, so we're going to be using up A. So we're going to be doing the forwards reaction. So we're going to be doing more of the forwards reaction. That means the equilibrium is shifting towards the products. So you've got more forwards, less backwards, in order to use up that extra A. Is anybody not happy with that, by the way? A shift to the products, a shift towards the products is a shift to the right. Good question. A shift towards the products is a shift to the right. And you can also, because it's laid out like this, from left to right, that's the forwards direction. From left to right is the forwards direction, always. And from right to left is the backwards direction. So if it's been written out for us, A plus B goes to make C plus D, then you know that that is the forwards direction always. So to the right is the forwards direction, to the left is the backwards, always. Lovely, good question. Okay, what about then if we increase C? I'm going to do this in green so that it doesn't, hopefully, doesn't confuse things. What about C? If I increase the concentration of C, what's going to happen to my position of equilibrium and why? Or can we explain why? What's that going to cause? So if I've got lots of C, I'm going to be using up that C. So I'm actually going to get an increase in the backwards reaction. And that means my equilibrium is shifting to the left. So an increase in C means more reactants are going to be formed. Which feels weird. I know that feels weird to say more reactants are formed because we think of reactants as being the beginning, but it's because we're thinking about the backwards reaction. But because these are written on the left, we still call them reactants, even if they are the product of the backwards reaction. It's a bit of an odd thing to get your head around. So lovely, equilibrium is shifting to the left. Oh, sorry, Jafar, I haven't seen your... Which answer, sorry? Your answer above, more for the blue, the increase in A, says more products formed to reduce the concentration of A. That's absolutely correct. Yes, I haven't seen another answer from you though, so do let me know if you thought you'd given one. So we're going to get a shift to the left. More reactants are going to be formed as the equilibrium is, or shifts, I should say, shifts to the left to redress the balance or to use up the extra C, or to increase the rate of the backwards reaction. We can say any of those. So more reactants are formed as the equilibrium shift to the left to use up the extra C to redress the balance. Okay. Let me know if you have any other questions. So blue is where we had an increase in A, it's going to shift to the right. And green is when we have an increase in C, it's going to shift to the left. Okay, what about temperature then? This is the one that often confuses people. So let's have a think about this. In an equilibrium reaction, if the forwards reaction is exothermic, the backwards reaction is therefore endothermic, and vice versa. This is a link. This is 100% all the time, happens all the time. If a forwards reaction gives out energy, then the reverse of that reaction must take in the same amount of energy. Hopefully it makes sense. It does, for me, it makes sense because you apply it in lots of different ways in A-level chemistry. So I think that's why it tends to make sense for me, because you then go on to use that principle, which means it makes sense. But if it doesn't, you can kind of think about it if you're a physicist, or if you know about vectors in maths. If you're walking between two spots, between A and B, if you walk due east 8 steps between A and B, then in order to get from B to A, we're going to have to walk the same number of steps, but back in the other direction. So it's the same principle here. If it takes an amount of energy to produce some products, then if I were to undo that reaction, I'd need to take in that same amount of energy. If I'm producing energy to produce products, I must need to take in that same amount of energy to get back to my reactants. So an exothermic forwards reaction will mean there is an endothermic backwards reaction, and it will be the same size, the same value of energy. So here I've been given delta H being enthalpy, or enthalpy change technically. I've been given enthalpy change is less than 0. If enthalpy change is less than 0, that means it's negative. The enthalpy change is negative, so the change in enthalpy starts somewhere and goes down. That means it must be giving out energy, so that must be exothermic. And then we might as well just do the other one while we're here. If an enthalpy change is greater than 0, that means it's positive, i.e. you started with an enthalpy, you've gained some energy, or enthalpy, sorry. So we have taken in enthalpy, then that must be endothermic. So that's talking about the forwards reaction. And because we've got that little enthalpy change written to the right of my products, we're saying the forwards reaction has that enthalpy. Okay, so in this case, on the left-hand side, our enthalpy change is negative. That means our forwards reaction is exothermic. So if we increase temperature with an exothermic forwards reaction, where is the equilibrium going to shift? An increase in temperature is going to shift which way? Yes, Tafara, very nice. An increase in temperature in an exothermic reaction, because exothermic also gives out heat. If we're increasing the temperature as well, it doesn't want to give out more heat because we've just increased the temperature. It wants to use up that heat. So it's going to go in the other direction, the endothermic direction. So increasing the temperature in an exothermic reaction shifts the equilibrium in the endothermic. Now, I'm going to be very specific and say endothermic backwards direction, because my examiner needs to know that I know the forwards reaction is exothermic, and therefore the backwards reaction is endothermic. It's a common missed mistake, common missed mark, unfortunately, where students say, oh, it's going to go in the endothermic direction, but nowhere have they been told explicitly which is exothermic and which is endothermic. And so as an examiner, I don't know that they know that, and I can't give them the mark. Okay, so if you're giving endothermic or exothermic direction, make sure that either in the question they have explicitly said the forwards reaction is exothermic. If they've said that, then it's fine. You can assume the backwards reaction is endothermic. So you can say in the endothermic direction, and they know you mean backwards. But if nowhere in the question does it say that, and it only gives you enthalpy data, then you need to make it explicit. Okay, otherwise you will lose a mark. So we're going to shift the equilibrium in the, or it shifts the equilibrium in the exothermic, i.e. backwards, no, endothermic, sorry, endothermic, i.e. backwards direction. You can also say to the left, you don't have to say backwards. You could say to the left as well, or towards the reactants. That's also fine because you're telling me which direction. So backwards, to the left, towards the reactants, any of those would be absolutely fine as long as you're telling me which direction it goes. Fabulous. What about to the on this right-hand one, when the forwards reaction is endothermic, if we increase the temperature again, funnily enough, it still wants to shift in the endothermic direction. So if it's the endothermic direction here is the forwards direction, then it's the same. It shifts the equilibrium. And again, I'm going to be very explicit in the endothermic forwards direction. Again, you can say to the right instead of forwards, and you can also say towards the products instead of forwards. That is totally fine, as long as you have explicitly told me which direction that is. Tafara, you have said endothermic, an increase in the temperature in endothermic forwards reaction, an increase in temperature will shift the reaction to the forwards. Yes, to the forwards direction, I would probably say, rather than forwards reaction, but yes, correct, well done. And OSA shifts the equilibrium in the endothermic reaction. So for the blue one, the endothermic reaction is to the left. In the green one, it is to the right. So you can either say to the right, or you can say towards the product. The blue one is to the left. The one on the example on the left is to the left. Anybody got any specific questions? Otherwise, we're going to need to think about moving on. Otherwise, we're not going to have time for exam questions at the end. I'm going to keep going. If you have any questions, just pop them in the chat. I think temperature is the hardest one. Let's finish up with think about a bit of pressure. Well, actually, not finish up. We have got one more to do, but let's just think about a little bit of pressure. So for gaseous reactants or products, so ignore solids, ignore liquids, because they can't produce pressure, or you can't change the pressure enough for it to make a difference. So for gaseous reactants or products, the position of the equilibrium will be affected by changes in pressure. So with this system, if we increase pressure, which direction is it going to go? Remember, we can ignore anything that is liquid or solid because they don't have a pressure or they don't have a changing pressure. So if I increase the pressure, which way is my equilibrium going to shift to reduce the pressure again? How's it going to want to reduce the pressure? Or what's it going to do to reduce the pressure? Yes, well done to Farah. It shifts to the direction with the fewer moles of gas. Very nice. So fewer moles of gas equals lower pressure. We'll come to why that is in a second, but you're absolutely right. It's going to shift to the side with fewer gas moles. Or fewer gas molecules, I should say. So there's only 1 mole of gas in the products. There are 2 moles of gas in the reactants. So there are fewer gas moles on the right-hand side. So an increase in pressure is going to shift to the side with fewer. An increase in pressure shifts the equilibrium to the right side. Again, you can say in the forwards direction. Or you can say towards the products, whichever makes more sense to you. As long as you're being explicit as to which direction that is. So we're going to produce more products. Whoops, didn't give myself enough space for that. So more products are going to be produced if we increase the pressure here. Conversely, if we decrease the pressure, funnily enough, it's going to do the opposite. So it shifts the equilibrium to the left. Again, you can say towards the reactants, to the left, in the backwards direction, whatever you want. So we're going to produce more reactants here because we're going to be doing more of the backwards reaction. Producing more reactants because there are more gas moles on the left. Now, where does this come from? This comes from the fact that we know that 1 mole of any gas at room temperature and pressure occupies 24 decimeters cubed. What that means is that any gas molecule, no matter the size of it, so it could be a massive molecule of butane, could be a tiny molecule of hydrogen gas, H2. Doesn't matter how big the gas molecule is, within our ideal gas law, we know that 1 mole of any gas occupies the same volume. So it doesn't matter what the gas is, it only matters how many moles of that gas you've got. So the more moles of gas you've got, the bigger the volume it is going to try to take up. And the bigger the volume it's going to try and take up, and if you're constricting it, you're saying, no, you have to only work within this reaction vessel, and it's this size, the bigger the volume it's trying to take up, the more the pressure. So if you've got 2 moles of gas, they're going to be trying to take up twice the space of 1 mole of gas, and therefore you're going to get twice the pressure. So we want fewer moles of gas so that they reduce the pressure. If we're increasing pressure, we're going to want fewer moles of gas. But conversely, if we decrease the pressure, then the system needs to fill the space that it's in. But in order to fill the space it's in, it needs to produce more moles of gas, because 1 mole of gas can only take up a certain amount of space. So if I decrease the pressure, the system is going to try to fill that space again with gas. So it's going to need to produce more moles of gas. So, decrease in pressure is going to shift to the left, and the increase in pressure is going to shift to the right, because there are fewer gas moles on the right. Okay, final bit then, and let me know if you have any questions. Final bit is, what is the effect of catalysts? How do catalysts affect the position of equilibrium? Anybody got any ideas? How do catalysts affect the position of equilibrium? They do. Do they affect the position of equilibrium? Catalysts, you're absolutely right, speed up the rate of reaction. So they help to reach equilibrium faster. But do they affect the position? No, they don't. Well done. Good, good, good. They help to reach equilibrium faster, but catalysts oh gosh, try that again. Catalysts do not affect the position of equilibrium. Let's try and spell that properly. Equilibrium. They do not affect the position of equilibrium. So you're absolutely right. Well done, everybody. They will speed up both the forwards and backwards reaction equally. So they don't just speed up one reaction to push the position of equilibrium towards the products or towards the reactants or whatever. They speed up both equally, which means we get to equilibrium faster. So if we think back to that graph we saw with the reactants, showing the reactants and products, and then reaching equilibrium, that would happen faster with a catalyst because we speed up the rate of reaction. So you're going to get more of the forwards and backwards reactions occurring, but it does it both directions equally. So we get to equilibrium faster, but it does not affect the position. Yes, it does indeed. It provides a faster route to complete the reaction. Yeah, lovely. Okay, how are we doing? We've just about got enough time to do some exam questions, which is great. So again, you don't have to share it, but it's nice if you do. But have a think about how you're feeling about those. We covered the content in enough detail as to what would be expected in an exam. So you shouldn't need to go into too much more detail than we did in an exam question in terms of why or what happens to the position of equilibrium, etc. But we'll have a go through an example just to prove it. But lovely, fabulous. If you're feeling good, that's awesome. If you're middly, that's absolutely fine. And if it's all a bit terrifying, again, totally fine. It just means you might want to take the opportunity to go back and think about some of your basics again, some of the core chemistry, make sure you're happy with all of the keywords, etc., before you come back to have a look at this. Okay. Awesome. Right, let's have a go at these exam questions then, because we've just about got enough time. So this says, in the catalytic converter of a car's engine, of a car engine's exhaust system, the following reaction occurs. Blah, 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 blah. And they've given us a piece of data. Might be useful, I'm guessing. The temperature in a catalytic converter is high. State the effect, if any, on the position of equilibrium if the temperature is lowered. Okay. Give a reason for your answer. So I'm going to decrease the temperature. I'm lowering the temperature. What's going to happen to the position of equilibrium? I'm going to give you a second to think about it before I jump in thinking through the answer. The temperature is lowered. What's going to happen to the position of equilibrium? Because they've asked for the position of equilibrium, I'm going to be saying to the right or left, probably, as my answer. And then my reason needs to be why I've chosen that one. Good. You're absolutely right, Tafara. And why? How do you know that? Okay, let's combine those two answers. So we've recognized that the Ford's reaction is exothermic because it's negative. So the Ford's reaction is exothermic. If I'm lowering the temperature, we're going to want to bring up the temperature again. The way I do that is with an exothermic reaction because that releases heat. So that's going to heat our reaction back up again. So I want the exothermic direction, which is the forwards direction. So that means it's going to be shifting to the right in the forwards direction. So the position of equilibrium, state the effect. The effect on the position of equilibrium is it will shift to the right. Why? Because that is yes, good, that is an exothermic reaction. Very nice. Because the forwards reaction is exothermic. And again, just calling back to what I said before, I need to state that because they didn't tell me that. They gave me data to suggest it was exothermic, but there's no statement anywhere, so I need to be the one that says the forwards reaction is exothermic. 2 marks, easy peasy. Hopefully we're going to have time for both of these. I'm not sure we are because we are running swiftly out of time. Let's ignore that one for now, then let's just skip straight on to part 3. State the effect, if any, on the position of equilibrium if the pressure on the reacting gases is increased. If the pressure is increased. So I'm going to flip back. So pressure is increased. Pressure is increased. What's going to happen? The pressure is increased. Which way is the equilibrium going to shift? And why? It is going to shift to the right. Very nice. Why? Good. Very nice. Well done. It is going to shift to the right, but why? Fewer moles. Very nice, Tafara. Lovely. Good team effort there. That was really nice. So the effect, again, we're going to shift. The position is going to shift to the right. But this time it's got nothing to do with exothermic or endothermic. We're talking about pressure. So we need to know about gas moles. So there are, as there are fewer moles of gas in the products. And if I wanted to, if I needed to, maybe they'd asked us for evidence or data or something like that, I could say 3 versus 4 if I wanted to. I don't need to though, but to the right, very nice, to reduce the pressure because there are fewer moles of gas in the products and that would reduce pressure. Very nice, well done. Okay, that just about brings us to the end, which is nice. Sorry we didn't get to do that 3rd middle exam question, but we're nearly there. I'm afraid I need to stop at 7. Sorry, guys. But we should now be able to understand the concept of reversible reactions and equilibrium, understand Le Chatelier's principle, and apply Le Chatelier's principle to different environmental changes. So again, like I said before, it's very similar to GCSE. It's just we need to be able to explain why. So we need to talk about number of moles of gas if needed. We need to talk about pressures, etc. So that's good. Right. Please, if you have any questions, I will hang around for a minute or two in case anybody does have any questions. But as I said at the beginning, this was my last YouTube video for SnapRevise. I'm going off to do other exciting things. But thank you so much thank you so much for engaging. And if you've been to any of the previous lives that I've done for SnapRevise as well, thank you very much. Please feel free to go back and have a look at all of the previous videos. I think they're all on the whatever the word is that I couldn't remember at the beginning. They're all on SnapRevise's. What is that word that my brain can't remember? Whatever it is. So no, the lives don't happen every day. There are Sunday sessions every Sunday in maths, physics, chemistry, and biology at SnapRevise, but I don't know what's going to be happening once I leave. This was my last YouTube class, so I don't know what's going to happen when I leave. So keep an eye out for the schedule anyway. Hopefully they will keep you updated. And have a lovely rest of your summer. Best of luck to those of you who have got results days coming up. Absolute best of luck. Hope you get what you want. Hope you get what you want. Cool. Thank you so much, guys. I will see you soon. Bye.